Okay, so please mute your microphone. Okay, so good morning once more, ladies and gentlemen, and welcome to HCIP IERS, Implementing Enterprise Network, Implementing Enterprise RS.
Routing and switching.
Routing and switching. So the very first topics za RS ni OSPF. Na hii topic ya kwanza, it's very interesting because it's the basics of OSPF. We're just going a little bit maybe deeper into some of the things, but most of the things, it's what you'll actually learn. Most of the things that you're going to learn in this topic is what you learned at the associate level. So it's just a reminder and going just a little bit deeper. Then in the subsequent topics, we're going to go even deeper. Okay. So OSPF protocol basics. So I'll read the forward. So the routing information protocol, RIP, is a routing protocol that is based on distance vector. Distance vector algorithm. So the disadvantages of RIP emerge when it is deployed on large networks. Why? We are going to see. And also an issue with slow convergence and poor scalability. So you cannot be able to grow, to expand, you cannot be able to grow in order to cater for the expansion of a large network. So we have another protocol known as Open Shortest Path Fast Protocol, which is a shortest path fast algorithm based. So that's the first thing. It uses SPF, and it's also a link state routing protocol, which was developed by the Internet Engineering Task Force, IETF. I hope you've already subscribed to IETF's mailing list. When you do such courses, you need to participate in IETF's matters. So OSPF can be deployed in large networks to overcome RIP's disadvantages. So how does OSPF meet network expansion requirements? So those are some of the things that we're going to learn in this particular topic. So let me ask request John to read for us the objectives. So by the end of this chapter, you should be able to.
One, understand RIP problems in large networks.
Yes.
Two, be familiar with OSPF characteristics. 3, master network types supported by OSPF. 4, master the process of establishing OSPF neighbor relationships.
Yes.
5, master the concepts and functions of OSPF DR and BDR.
BDR, very well. Okay, so the very first thing we're going to look at is challenges that RIP is confronted with in large networks. Then we can look at the basic principles of OSPF. Now, we have several changes that have occurred in the recent years in large networks due to the emerging enterprise services, such as what we are using right now, live online learning, virtual learning. So networks are generally expanding due to some of this popularity of social media sites and so on and so forth. And even within companies, more and more companies are now embracing, especially due to COVID-19 and even before. Most companies are already doing virtual meetings and so on and so forth, voice over IP and such like applications. So such applications require high network reliability. That means that in case failure occurs within the network needs to recover within the shortest time possible, so that it does not disrupt the normal working. Like right now, if our internet go down, you see, it really disrupts our learning. So networks require high reliability. And now we also have a trend towards heterogeneity of networks. A trend towards heterogeneity of networks. What that means is, most of the time, you'll get that you have multi-vendor devices that belong to different vendors. You need devices that belong to different, you have devices that belong to different vendors. So you have a Huawei device, you have a Cisco device, and so on and so forth. And therefore, most of the time, you need a protocol that is widely acceptable and implemented by a majority of the vendors. So let's look at can RIP be able to meet this requirement? The requirements of that we've looked at: high reliability, supporting multi-vendor devices, being able to recover from failures very fast. Can RIP be able to meet that particular problem? Now, these are some of the existing problems with RIP in large networks in particular. One of them is what we call the hop by hop convergence. Hop by hop convergence. So what this means is, if a failure occurs here at N1, RTA is going to alert RTB, then RTB is going to alert RTD, so on and so forth until it gets to RTE. So that is what we call hop by hop convergence. So this results into slow convergence and a long failure recovery time. Remember, we've said that large networks need high reliability and fast recovery from failures. But now with slow convergence, it becomes an issue. So that's one of the issue with RIP. The other issue with RIP is what we call routing by rumor mechanism. So RIP does not understand the global network topology. It does not understand the global network topology. When we were being trained by a very good instructor called Mr. Tony Hu, he gave us the analogy of RIP as being the physical addresses. Imagine you want to travel from Kitale to Nairobi for the first time, and now you are following the physical, are they called addresses or signs? The signs. So when you get to Eldoret, you look at the sign, then it tells you go this way. You get to Nakuru, you look at the sign, it tells you go this way until you get to Nairobi. So that is how RIP really works. So it does not understand the global network topology. Now, when you talk of the global network topology, think of it like using Google Map to travel from Kitale to Nairobi. So you'll simply do a search, and in your phone, you can be able to see the entire route from Kitale to Nairobi, and you can even see several routes, and you can be able to follow a route that is more reliable, maybe the shortest route. So with RIP, it is routing by rumor. So you don't need to understand what is happening at this network segment, no. All you need to do is, hey, you've received a packet, you know you're supposed to pass it to this guy. So this guy will receive it, know whether they're supposed to pass it to this guy or that guy, like that. So that is what we call routing by rumor mechanism, which is not very efficient, as you're going to see with OSPF. Okay, and then we have another problem, which is the maximum available number of hops is 15. So if you read about RIP, you know that you cannot use more than 15 routers in RIP. So it is not scalable. It's not scalable. So most networks nowadays involve more than just 15 routers. So it cannot expand. It cannot expand very well within a network. Then the other one is it uses hop count. It uses hop count to measure the distance to a destination. So that means that if you want to send a packet from network 1 here to network 2, then RTA is going to forward the packet using the path that has the fewest number of hops or fewest number of routers. So for example, here we have 1, 2, 3, 4. So it's going to follow that path. Even though, for example, if it followed 1, 2, 3 RTC, 4, 5, the packet will arrive faster at N2. Why? Because we can see that the link between RTB and RTD is a serial interface, which is very slow compared to Ethernet interfaces. So generally, if this packet was to be forwarded via RTC, it will arrive faster. It will arrive faster. So with RIP, it cannot be able to make such a decision because it forwards based on the hop count and not based on the link bandwidth like OSPF. So this can lead to what we call suboptimal routes. Okay. So how can we solve some of the problems we've identified there? So the first one is on slow convergence and long failure recovery. So we saw that the convergence is done hop by hop, and what really happens is it does this. A router receives an update. For example, a link has gone down. Then it calculates a new route, then sends the update. So that can be changed so that it's a little bit faster like this. So you receive an update that a link has gone down, you receive it from another router, share it with the next router, share that information with the next router before calculating your routes, before calculating your new routes. So that can indeed speed up the recovery time a little. Okay. Then the second problem is on lack of view of the global network topology. I think this I have already explained. So the solution is a router can independently calculate routes on the basis of the topology information. And therefore it means that the router can be able to see the entire topology. So that is really what happens in OSPF and in other link state protocols, as we are going to see. So we're going to see when you look at the subsequent topics, we're going to see how a router is able to learn about the entire topology of the network. Okay, and then we have the other problem, maximum available hops, 15. So the solution is just ensure that we have unlimited hops. Then the last one is a risk of selecting suboptimal route. So use the link bandwidth as the criteria for route selection. Use link bandwidth. Okay, so these are the problems of RIP again. Now, how do how do the link state routing protocols solve these problems? So RIP, let me just, RIP falls under what we call distance vector. It's a distance vector algorithm protocol. Then the second type is now what we call link state routing protocols. So in link state routing protocols, we have OSPF. We're also going to look at what we call IS, and even BGP uses link states. So RIP uses distance. It's a distance vector routing protocol. And by distance, we talk of number of hops. So that's why even in version 2.5 of HCIA routing and switching, we did not learn about RIP because most networks are phasing out RIP. And over the recent years, it is seldomly used. So RIP, all protocol, because of all those problems we've looked at. Now let's look at link state protocols and how they solve that particular problem. In particular here, we are referring to OSPF. Okay, now it is first of all important to understand what the term link state means. Link state. Link state. So link state is actually the status of the interfaces on an OSPF router. The status of the interface of an OSPF router. Now, this status can include a number of things. We are going to look at some of them in details, but one of them, for example, is the link type. I'm going to explain to you what the link type is, but we also have the IP address of that particular interface and the mask. We also have the bandwidth. So what's the bandwidth of that particular interface? Sorry, the bandwidth. We also have the neighbor, the neighbors, the neighbor that particular interface is connected to. So these are some. So when you talk of link state, I want you to understand that these are some of the things that we are referring to about the link. So the link is simply the interface that is connecting the router to another router or to a shared network segment. So link state. Okay, so I'm going to expound on that much further in a coming slide. So the first thing OSPF does is to separate routing information propagation from route calculation. So what OSPF does is that it transmits link state information to the neighbors instead of transmitting its complete routing table. So I've told you that the link state is the link type, the link bandwidth, the IP address on the mask, and the neighbors who you are connected to. So that is what we call link state information. So you send that information to your neighbors. Once you send that information to your neighbors, now they can be able to calculate, to know everyone else that is on that network and who you are connected to, and they can be able to calculate their own path to each of the persons that you've shared. So that is what we call routing information propagation. So routing information propagation is done or achieved using what we call link state information. So you share the link state information with your neighbors. Then each of the neighbor now can do their own route calculation. So that's number one. Number two, it uses the shortest path first algorithm, SPF. We're going to look how routers calculate SPF, but in particular, I want to mention that when a router is calculating SPF, it actually does this by assuming itself as the root. So you are calculating distances to all other people from you as the root. So we are going to create what is called a shortest path tree. And you're going to see how this really means and how it's done. And this will generally speed up also the network convergence speed. Okay, and then lastly, OSPF uses what we call the accumulated link cost. So instead of using the number of hops, it uses the accumulated link cost as the criteria for route selection. So accumulated link cost, it means we are taking the bandwidth. We are taking the bandwidth of each of the interface from source to the destination, the outgoing interface on each of the router. So that is what we call accumulated link cost, because we are adding each one of them. I think we're going to see that in the next in the coming slides shortly. So this is what we call link state information. So link state information are simply, hey, I know Kitale, I know Kisumu, I know Nairobi, I know Mombasa, I know like that. So every router is going to share and say, hey, I know how to go here, I know how to go here, I know how to go here. And now, by them sharing what they know, that process is called LSDB synchronization. And now every router is going to have the entire map of that particular network. So LSDB is link state database. So link state database is what is used to store that particular information that is being shared by all the routers in that particular network. Okay, so let's look at the OSPF working process. I'm sure we did this during the associate level, but we're just going through it again. Generally, OSPF can be, the process of OSPF route calculation can be summarized in 3 steps. The very first step is what we call the establishment of the neighbor relationship. Then number 2 is to share the link state information. So we call that synchronizing the link state databases. And after sharing that, then you're able to now calculate the optimal routes using SPF, shortest path algorithm. So when you're using shortest path algorithm, you actually create a shortest path tree with yourself as the root. So we are going to go through that process in a short while. What is a neighbor relationship? Neighbor relationship is simply discovering who your neighbor is and introducing yourself to your neighbor. So those are other routers. Synchronization of LSDBs is simply sharing the link state information. I know this, I know how to go here, I know how to go here, I know how to go here, and so on and so forth. So let us now look at each of these processes in detail. So neighbor relationship establishment. Now in an OSPF network, every router must be identified with a unique number called the router ID. We're already familiar with the router ID, but now I just want to emphasize that the router ID is a 32-bit unsigned integer, which has the same format as an IP address. So every router in your network must be uniquely identified by a router ID. Now, the router ID should be unique within the autonomous system, the AS. We already know what an autonomous system is. So within an autonomous system, each router must have a unique, it must have a unique router ID. Now, let me ask at this point, do you still recall the criteria to selecting a router ID from the associate level? So how does the router select a router ID? Can one of you share with us what you remember?
By manually configuration of the router ID first.
So that's the very first one. Manual configuration.
If it's not configured, you get the loopback address also.
Yes, the largest IP, IP address on any of the loopback interface.
And if that is not the case, it gets the highest interface IP address.
Exactly, physical interface. So the largest IP address of any of its active physical interface as its router ID. And among those three ways, which one is the most recommended?
The manual configuration.
Manual, exactly. So we've said that the first one is manual config. You manually configure router ID, which is the one that is recommended, or it will take highest, or you can call it largest IP on a loopback interface, or lastly, it can also take largest IP on a physical. It has to be active. That means the status has to be up, physical interface. So it's important that you remember that. Now, in case you configure a new router ID, what must be done in order for the new ID to be applied on the router? So for example, this router here, let's say it's RTA. It had a router ID of 1.1.1. So what must be done? What must be done in order to apply the new router ID? Donald, if you can disable your video, please. So you must reset the OSPF process. You must reset the OSPF process for a newly configured router ID to take effect. Newly configured router ID to take effect. So don't forget that. It's a very common question in the exams. Okay, so let's move on.
Does that mean also the router is reset, physical reset of the router?
No. You're not resetting the entire. You're not restarting the entire router. You are simply resetting the process. See, each of these configured protocols in a router is a process. A process is like an application. Like right now, I'm using PowerPoint to teach you. So when I close PowerPoint, I've not shut down my laptop. So a process is like an app when you've opened an app. So you have to reset that particular process, the OSPF process. Okay. Now, the neighbor discovery, a neighbor relationship establishment, uses a packet, an OSPF packet called the hello packet. the hello packet. I know you can still remember the 5 OSPF packet types. Other than the hello packet, which other packet types do we have? Someone just enable your mic and tell us one of them. Then I can note them down.
LSU.
So, just a moment. OSPF packet types. So we have hello. Another one, anyone? What did you say, Alan?
LSR, LSU.
Link state update and link state request. Someone else?
Database description.
DD, database description. Anyone else? The last one?
LSAC.
Exactly. Link state acknowledge. Link state acknowledge. So the very first OSPF packet type is hello packet. It performs the following 3 functions: neighbor discovery, neighbor relationship establishment, and maintaining neighbor relationships. So discovery, an OSPF router can send a hello packet to discover the other neighboring routers. On establishing the neighbor relationship, 2 OSPF routers will negotiate, this is important, parameters in hello packets to establish a neighbor relationship. So in the coming slides, we're going to see some of the parameters that are negotiated. Then in order to maintain OSPF neighbor relationships, it uses what we call a keep alive mechanism to continually detect the neighbor reachability. So if a router does not receive any hello packet from its neighbor within a specified period of time, then the router will terminate the OSPF neighbor relationship with that particular neighbor. So that is how the keep alive mechanism actually works. If you don't receive hello packet for a certain amount of time, predefined amount of time, you simply terminate that neighbor relationship. Okay. So let's look at the first function of the hello packet, which is the OSPF neighbor relationship establishment. This happens through a number of states. So we have down. So we have down here, number 2, we have init for initialization, and we have two-way. So these are the three steps that are involved when it comes to neighbor relationship, the 3 states, neighbor states that are involved when it comes to establishing the neighbor relationship. Okay, so let's go through it. So here we have 2 routers, RTA and RTB. And the router ID is 1.1.1. The router ID here is 2.2.2. Now, I want to make a comment here that in the labs, you'll get that the router ID for RTA is 10.1.1, like that. But for me, when I configure router IDs, I like configuring router IDs with the number of the router. So if it's R1, I'll configure 1.1.1.1. If it's R2, I'll configure 2.2.2.2 as the router ID. And I want to advise that you do that in all the labs, because when you configure something like this, it looks like the interface addresses. Because you'll get that in the same topology, you have a network maybe whose address is 10.0.1.2 or something. So it becomes quite difficult to differentiate between the router ID and the interfaces or the loopback IP address. So most of the time, please make sure that you configure a router ID using the router ID number. So if it's router 1.1.1, like that. Okay, so let's look at these states and what they mean. So the first state is down. So the down state is when you've not received any information from your neighbor. So for example here, RTA is sending a hello packet to RTB. The contents, the parameters it's sending is, I'm identifying myself. So I'm sending the router ID, and on the neighbor list, my neighbor list is empty. So I don't have any neighbor. So when RTB receives this information from RTA, it will transit from the down state to the init state, because now it has received a hello packet from a neighbor. Now, at almost the same time, RTB will also send a hello packet. It will also send a hello packet to RTA, and also RTD. It sent this hello packet before it received this one maybe. So it does not know any neighbor. So the neighbor list is also empty. So when RTA receives that particular packet, it will also transit to the init or initial state. Okay, then step number 3 here is now RTB is sending a hello packet to RTA with RTA's router ID on its neighbor list. So meaning that RTB has already learned about this neighbor. So when RTA receives this hello packet with its own router ID in RTB's neighbors list, then it transits from the init state to two-way state. At almost the same time, RTA will also send another hello packet to RTB with RTB's router ID on its neighbor list. And when RTB receives that, then it's going to transit from the init state to the two-way state. Now, it's only when you are on the two-way state that we say that you have achieved what we call bidirectional. This is important, bidirectional communication. See, some of these terms I'm insisting on, you're going to get them in the exam. So it's only on two-way state that you can achieve bidirectional communication, because you know this neighbor and the neighbor also knows you, so you can be able to start communicating. Otherwise, at the init state, you cannot do bidirectional communication with your neighbor. Okay. So that is it about the neighbor establishment process. Let's look at the next one, the neighbor discovery. There's something I didn't mention. Now, when RTA, there's something I didn't mention here. When RTA is sending, this particular hello packet, we are sending this hello packet in the network. You are sending that particular packet, OSPF packet, as a multicast packet. And this particular multicast packet is destined to all OSPF routers, all routers that have been configured to listen on OSPF. And the destination is normally the multicast address 224.0.0.5. So I didn't mention that, multicast. Now, we have certain network types that do not support multicast packets. We have certain network types that do not support multicast packets. So what happens? Does it mean that OSPF cannot work in such network types? And if OSPF can work, then how do routers establish neighbor relationship? The answer to that, through what we call manual configuration. Through what we call manual configuration. So OSPF routers, OSPF allows routers to establish neighbor relationships using unicast. Unicast. So the other one was multicast, but you can also use unicast hello packets. So if the network does not have the multicast capability, neighbor relationships must be manually established. So how to do that? So you've connected these two routers, RTA, RTB, over a network that does not support, for example, multicast. So if you want to manually establish the neighbor relationship, you use this command. So you go to the OSPF process, so OSPF1, then you use the peer command. So peer, then the IP address of the interface of your neighbor to which you're connected to. So we simply enter the IP address, only the IP address and not the mask. So peer, then 10.1.12.2. Then you also have to do the same on RTB. Yeah. So that is how manual configuration is done. As with all other manual configurations that we've talked of, even at the associate level, what do you think are some of the problems that are associated with manual configuration?
tedious,
Exactly. Tedious. Number two,
bound to errors, forgetting.
exactly. Ukichoka, most likely you're going to do errors. So those are the two most problems that are associated, two common problems that are associated with manual configuration. Okay, so the purpose of establishing neighbor relationships is so that routers can be able to exchange their link state information and therefore synchronize their LSDBs. So let's see, how is this synchronization done? How is the synchronization achieved? So this is a link state protocol. Some of the link state information include the link type, the IP address, and the subnet mask. I had mentioned this, the neighbors you're connected to on the same link, and also the cost, the link bandwidth cost. So you are supposed to understand, each of this and what they mean. So let's look at the link type. What is the link type? Now, extensive data link layer support. A variety of data link layer protocols exist, and their working mechanisms differ. Now, application scenarios of various data link layer protocols must be considered in order to support these protocols. So different kinds of physical links have their unique characteristics. So you see, like in this network, we have a serial connection between this router and that router. Then these routers here are connected via Ethernet cables in a multi-access network. These routers here, these ones here, are connected over a frame relay switch using frame relay. So they operate differently. Therefore, a mature routing protocol must fit the characteristics of a physical link where it is applied. With that in mind, OSPF defines a number of network types. So let me start by asking again, how many network types does OSPF support? Anyone who can remember?
Point to point.
How many How many in total?
Four of them. Four.
So four OSPF network types. So can someone else mention another one? So Alan has said point to point. Another one?
Broadcast.
Broadcast. Then
NMBS.
NBMA, non-broadcast multi-access. And the last one? It is almost related to the first one.
Multi-point.
Exactly.
Point to multi-point.
Point to multi-point. So these are the three network types that OSPF, the four network types that OSPF supports. And now OSPF is going to behave differently in each one of them, depending on the characteristic of that particular link type. Now, let's begin with point-to-point. Point-to-point is normally thought of as two routers connected to each other. And a good example is when two routers have been connected to each other using a serial link. Because when you use a serial link, you're going to use the point-to-point protocol, PPP, between the two routers. Now, there are two important things to note about each of these network types. One of them is, does it support broadcast packets? Number two, does it support multicast packets? So with point-to-point, it supports both broadcast packets and multicast packets. And the last thing now to note is, do we have elections? Do we have an election of a DR and a BDR in that particular network type? So if you can remember, in point-to-point, do we have an election in point-to-point networks?
No.
We don't. Why do you think that is so? What is the purpose of the election, by the way?
To elect a BDR and DR.
Why? Why are we electing a DR?
To avoid flooding, LSF flooding.
Exactly, to avoid, reduce the adjacencies. But now, if we are only having two routers, are we having any adjacencies that we need to sort? No. So we don't need an election in point-to-point networks because of that particular reason. Okay. So let's move on to broadcast networks. So with broadcast networks, it allows two or more devices to access the same shared link. Two or more devices to access the same shared link. Now, just like in point-to-point networks, in broadcast networks, it supports broadcasts. It supports broadcast and multicast. Now let me ask, in broadcast networks, do we have elections of a DR or a BDR and a BDR, sorry?
Yes.
Yes, we have, because we need to reduce the adjacencies. Everyone sharing with everyone else. So here we have an election. Now, most of the time, when you use an Ethernet cable, to interconnect routers, they automatically are thought of as being a broadcast network type in OSPF. So while serial cables take point-to-point, broadcasts take Ethernet take broadcast network type. Okay, then the next one here is the non-broadcast multi-access broadcast multiple access network. A broadcast multiple access network uses, as you can see here, it uses virtual circuits to interconnect the routers. Uses virtual circuits to interconnect it uses virtual circuits to interconnect the routers. So for example, when you're using frame relay, so you have to use virtual circuits, and this is what we call a frame relay switch. So this is the headquarters, and these are your branches, RTB, like that. So you configure virtual circuits using what we call DLSI numbers. So we didn't, if you did version 2.5, we didn't learn about frame relay, but I can still show you how it works through the configuration of a cloud. In fact, you can watch my YouTube video on configuring a cloud. It's just the same thing. Just the same thing. If we're using a cloud here, it's just like we're using a virtual circuit. So a non-broadcast multi-access network, a good example is what we call a fully meshed frame relay network. So everyone is interconnected with everyone else. So you see here, you have 3 routers and you have 3 virtual circuits. So that's why it's called fully meshed. So you have a virtual circuit that is interconnecting RTB and RTA, another virtual circuit interconnecting RTA and RTC, and also you've interconnected RTB and RTC through this virtual circuit, this one. So it's called a fully meshed. Now, it is important to note that neither broadcast packets nor multicast packets are supported, not supported, in non-broadcast multi-access networks. So how are neighbor relationships, OSPF neighbor relationships formed if multicast packets cannot be shared? Anyone can give it a try? In NBMA networks, how? How do they establish neighbor relationships? Anyone? Okay, so we just looked at that command. For example, OSPF1, then peer. So peer, if for example we are in RTA, peer 10.1.1.3.3. Then again you do peer 10.1.2. So this is in RTA, for example, in RTA. So neighbors must be manually specified. Why? Because multicast broadcast packets are not permitted. Do we have elections in non-broadcast multi-access networks for a DR and a BDR? Hello, can I be heard?
Yes, we have. Yes, we have.
Exactly. So we have elections in NBMA. Okay. Then point to multipoint. Point to multipoint is a set of multiple point-to-point networks. It almost looks like like NBMA, but this one is not fully meshed. It is what we call partially meshed frame relay network. So if RTB wants to communicate to RTC, they have to do so via RTA, because we don't have a direct virtual circuit between RTB and RTC. So it's called a partially meshed frame relay network. Here, broadcast and multicast are supported. And therefore, OSPF neighbors can be discovered Normally, here neighbors are discovered using what you call inverse ARP. Reverse ARP, address resolution protocol. So you can note that down so that you go and read further and understand how that is done. So generally, those are the four. Those are the four network types that are supported in OSPF. Now let's look at the OSPF cost. Now the OSPF cost is normally calculated using what we call the reference bandwidth formula. The reference bandwidth formula goes as that the interface cost is equals to the reference bandwidth, which is normally set to 100 megabits per second. 100 megabits per second, all over the bandwidth of that particular interface. So what does that mean? That means that we've said that the reference bandwidth is normally 100 Mbps. So if an interface, sorry, if you lose me at any point, one of you can always call me. Maybe Alan. Alan, you can be the acting class rep.
Gadud is good at that.
Because sometimes I'm called. Gadud, you can also help me. Please help me. Sometimes someone calls me and I'm disconnected or something without being aware. Okay, so for example, if an interface has a speed of 10 megabits per second, 10 megabits per second, then the speed for that particular interface is going to be, the cost for that interface is going to be 10, right? It's going to be 10. Similarly, if the speed of an interface is 100 megabits per second, then the cost is going to be 1. On the other hand, if it's 1000, the speed of an interface is 1 gig. It's a gigabit Ethernet. What is going to be the cost using the default reference bandwidth?
1.
Exactly. So it's going to be 1. So generally, if you divide 100 by 1000, you're going to get 0.1. But anything that is less than 1 is normally rounded up. To 1. So generally, we say that the default reference bandwidth does not offer us very accurate metrics. So that's why the reason that's why this was the default is because when they came up with this formula, the maximum speed for any interface was 100 Mbps. But now we have interfaces that can do 1 gig, 10 gig, even 40 gig. So you can always configure and change in your router the default reference bandwidth, so that this does not give you 1 and also this one gives you 1. It means they have the same cost, which is not true. This interface is faster than this one. Okay, so now the cost can be changed in 2 ways. Number 1 is to configure the cost directly under the interface mode. So you can go to an interface, then use the command OSPF space interface 20. So you'll specify the cost for that particular interface as 20. OSPF cost 20, something like that. So that is on the interface mode. So for example, you go to this interface G1 and you use that command. So the interface for that will be 20 if you do that. Then you can also change the reference bandwidth, which is just what I talked about here, that you don't want to use the default reference bandwidth because it's not accurate. Now, it is important to note that when you do this, you must do it on all the routers in order to ensure route selection consistency within your network. No? So kila mtu lazima abadilishwe in your autonomous system. Now, the other important factor to understand is accumulated cost. So OSPF metric is what we call a cumulative cost. That is the total cost of all outbound interface. So if you want the cost from RTA to this network segment, it is the total cost of all the outbound interfaces. So G1, the cost of G1 plus the cost of G3. So that is what is going to give us the total cost of arriving to this network. And we don't add the cost that is connecting to that network. So we don't add that particular one. We don't add this one. So we don't add that cost. We only add this one and this one. So I hope you understand what I mean there. So OSPF actually takes into account both the bandwidth and the hop count. Because when you do accumulated cost, there's no way you can use the longer hop. There's no way you can use the longer hop, because the longer the hop, the more the cost, because you're using a cumulative cost. So it's important that we understand that. Okay. Now let's look at how, let's look at OSPF packet types and how they function. So we begin that by looking at the OSPF packet header. To begin with, I want to mention that OSPF operates at layer 3 and is encapsulated by an IP header. It's encapsulated by an IP header, and on the IP header, the protocol number field for an OSPF packet is 89. Now, all those OSPF packet types, the 5 packet types that we mentioned, all of them must have an OSPF packet header. And the packet header, so the first part of an OSPF packet, the first part of it is the header, then the second part is the data. Now, at this particular point, we're just looking at the fields of the OSPF packet header. So all of them must have this. All of them must have the header. Now the header, the first field in the header is the version. Of course, version specifies the version of OSPF. Here we are using version 2. Version 2 works on IPv4 networks. If you learn HCI, I think at some point maybe we might learn it in this course and also in HCIE, but we also have version 3 that supports IPv6 networks. Then we have the type. So this is where you specify, this is where the OSPF packet type is specified. So is this an LSR? Is this an LSU? Is this a DD? What type of packet is it? Then here, the packet length is the length of the entire OSPF packet. The length of the entire OSPF packet in bytes. So the length of both the header and the data that it carries in bytes. So that's the packet length. The router ID is, I think, self-explanatory. Is simply the identity of the router that has originated this packet. Area ID is which area has this packet been advertised. So it will give the number there. Checksum, just like in many other headers that we've looked at, is used for verifying the data integrity of the OSPF packets, including the header. Then the authentication type, if you can remember, when we were learning HCIA, we said that OSPF version 2 supports 3 forms of authentication. The first one is, we call it no authentication or none authentication. So it supports none authentication. Now let me use Let me use the value 0 here. 0. Then 1, we have also what we call simple password. And lastly, we have cryptographic authentication. So this particular field here, auth type, will have a value 0 if you've not configured any form of authentication. It will have a value 1 if you're using simple password authentication. Have a value 2 if you're using cryptographic authentication. Then the other fields here will differ depending on the type of authentication that you're using. So that is what that carries. So I hope you've understood the OSPF header, and it's important to understand that all OSPF packets will have this header. Now let's look at the OSPF packet types. Can one of you read for us the first one there? Winnie, are you there? Is Winnie here, by the way? Let me check. Okay, Eric, read for us the first one there.
Hello.
And what is it used for?
Discover and maintain OSPF neighbor relationship.
Yes, to discover and maintain OSPF neighbor relationships. I think we've said that. Donald, help us with the next one there. Okay, Gadudi.
Hello, Kari.
Yes, Donald.
Hello.
Hey.
Yeah, I'm in the office, so you just bear with me today.
Okay. Sawa. Okay. Gadudi.
Okay.
Database description
Mm-hmm.
to exchange LSDB summary.
Yes, to exchange the summary information. Macau.
Link state request to request specific link state information.
Read for us the next one, Macau.
Link state update to send requested link state information.
Okay. And lastly,
link state acknowledgement, LSAC, to acknowledge receipt of an LSA.
Exactly. Thank you very much, Macau. Okay. Now, sometimes we'll also be talking of type 1 OSPF packets, type 2, type 3. So it's good that you associate the number with the name. The number with the name. So when I talk of a type 5 OSPF packet, I'm talking of a link state acknowledgement. So you should know it. Okay, so most of these things, we already discussed them at HCIA level, but just as a summary, database description used during the exchange of the summary link state information of each network. Request, by summary we say, when routers are exchanging routes that they've learned, they simply send the summary. So for example, I say, hey, I know Kitale. Hey, I know how to go to Kitale. I know how to go to Nakuru. I know how to go to Eldoret. So that is what you're sending to your neighbors. Then your neighbor will check, do I know how to go to Kitale? No, I don't know how to go to Kitale. So the neighbor is going to send a link state request to me. Hey, Karis, please tell me how to go to Kitale. So the request is sent using link state request. Then I'll send you back the detailed information on how to go to Kitale. So I send that using the link state update. And once you receive that detailed information on how to go to Kitale, you now send me back the link state acknowledgement, acknowledging that you've received my update. So generally, that is how these packets are used in OSPF. And we're going to have a look at them more and more. Okay. Oh, okay. So let's look at the functional requirement of OSPF packet. Functional requirements. So function to be achieved. Here we are looking at neighbor relationship and discovery. So we use the hello mechanism to do that. So for LSA synchronization, so enable two routers to send LSAs. So an LSA is a link state advertisement to each other for LSA synchronization. LSA synchronization is fast and fewer resources are consumed. So that is that. And then the other function that we need to achieve in OSPF packets is reliability. So ensure reliable LSA synchronization. So by faster and reliable, we mean what I just explained. You first of all send the summary information rather than the entire detail about the route that you know about. So that is how that is done better than in RIP. Now let's look at the LSDB synchronization process. So after establishing the neighbor relationship, you can proceed to achieve the other states. You remember in neighbor relationship, we had talked of the down state, we had talked of the init state, and we had talked of the last one there was two-way, right?
Two-way.
Exactly, two-way. Now, we also have other states. 1, 2, we are going to say them, 3. So we also have what we call extat. The extat state, we have the exchange state. Number 6, we have the loading state, and lastly, you have the full state. Okay, so I just want you to understand what is happening here. So we have RTA, RTB. They're already on two-way state and they have achieved bidirectional communication. So what happens at the extat state? Now the extat state, the two routers try to establish what we call a master/slave relationship. And they also determine the initial sequence number. It is important to note that at the extat state, we do not exchange any link state information. So extat state, let's look at it. So at extat state, R1 here, RTA is sending a DDD packet to RTB. So what it does, it actually generates a sequence number. Sequence number ni kama ID ya identify uniquely each message. So it identifies a sequence number, for example, X. Then it also sets some 3 bits here, the I bit, M bit, and MS bit to certain values. So that is what we call the extat state. Majorly at the extat state, they determine the initial sequence number and also form a master and slave relationship. So when you talk of a master and slave relationship, how is that achieved? How is that achieved? Now let me talk to let me highlight this. So we have the router ID. We have the router ID here. Now, whichever router that has the largest router ID becomes the master. Becomes the master. Now, we have those 3 bits. So we have I bit, we have M bit, and we have MS bit. MS bit is what we call the master bit. So when this is, when talk of the master bit, when it is 0, it means not master. Not master. When this is 1, it means I'm master. I'm the master. So initially, when RTA is sending this particular first DDD packet to RTB, it will set the MS bit to 1, meaning I am master. So everyone initially asserts themselves as the master. So that's the master bit. Okay. Now, after that, RTB, almost at the same time, will also send. I'm going to talk about the I bit and M bit in a short while. So this one is also going to send a DDD packet to RTA. Now, when RTA receives the DDD packet from RTB, RTB will have also generated a sequence number for the DDD packet and also assert itself as the master. So when RTA receives that DDD packet from RTB, it will transit from the extract to the exchange state. Now, in the exchange state, the routers will exchange DDD packets containing the link state summary information with the neighbor. Now, after RTA receives this particular DDD packet, it will look at the router ID of RTB and see, oh, this guy has a better router ID. And therefore, it's going to send a DDD packet with the sequence number similar to the sequence number of the packet it received from RTB, meaning that, hey, you guy, you are the master. So when RTB receives that, then it's going to transit from extract to exchange. And now you can see that from then henceforth, RTB is going to be the master. So now, in the exchange, I've said that at the exchange, the routers are now exchanging the link state summary information with the neighbors. So here, for example, RTB is telling RTA, hey, I know Kitale. I know Kitale. So you see, it will update its sequence number with 1. Venye tu nimwambia, sequence number is simply an ID. So for example, 2030. So the next one is going to be 2031, 2032, like that. And it's going to set its MS bit to 1 because it's the master. Now, after that, when this RTA receives a DDD from RTB and sees that, hey, RTB knows how to go to Kitale, but I don't know how to go to Kitale. So RTB is going to send a request. Hey, RTB, tell me how to go to Kitale, like that. So that is really what happens during the exchange. Now, during the loading state, you can see now we are transiting here from exchange to loading. So this is now where we exchange the LSR, LSU, and LSAC. So we can send a link state request. So here, RTA is sending a request. Hey, tell me about Kitale. then this guy will reply, hey, this is how you go to Kitale, like that. Then this one will reply with an acknowledgement, hey, thank you for telling me how to go to Kitale, like that. So it is in the loading state where these routers will exchange LSR, LSU, and LSAC packets. So after they've exchanged all their routes, they now transit from the loading state to the full state, meaning that now everything that RTB knows, every route that RTB knows, RTA also knows. So that is what we call the full state, the full state. Okay, so any question here before I talk about the M-bit and the I-bit? Okay, now the I-bit, you see the first DDD packet that RTA is sending to RTB, the I-bit is set to 1. That's why you can see that the I-bit is included there. The reason as to why the I-bit is set to 1 is because the I-bit is used to indicate the first DDD packet. So I-bit used to indicate the first DDD packet. It simply means that this is the first DDD packet, and therefore it's going to be set to 1. So if it's not the first DDD packet, then it's not going to be set. So that's why you can see in these other packets like number 3, number 4, number 5, we don't have the I-bit set because this is not the first. Then the M-bit, the M-bit is used to indicate that we need more DDD packets to be sent. So it simply means that this is not the last. Something like that. Indicate this is not the last DDD. This is not the last DDD. So we need more DDD packets to be sent. So that is when the M-bit is set to 1. So that is the I-bit, M-bit, and MS-bit. Okay. So let's look at the synchronization process. Step number 2. So at loading, so I've already explained this. During the loading state, you send link state request, you get a link state update, you acknowledge, and when you have everything that is needed between the two of you, then you transit to the full state. Now, it is important that you understand each of these states, because in case you have incorrect configuration or link failures, then you'll have to troubleshoot. And in order to be able to identify the problem faster, you need to understand each of these states, because most of the time you'll see where the failure occurred, at what state did it occur. So at that particular point, then you'll be able to know what the problem might be. And the very last OSPF lab you're going to do is going to be on troubleshooting. And you're going to see how that really happens. So this is how the neighbor state machine looks like. The only state that I have not talked about here so far, is the attempt state. This only happens in the NBMA networks in order to establish whether the virtual circuit is active, whether you're able to reach the other person. So the attempt state. But otherwise, for the other states, I think we've already discussed them thoroughly. So from down to init, after you've received a hello packet, and then when you receive a hello packet with your router ID in the neighbor list, you transit to two-way. Exstart, you negotiate the sequence number and who's master, who's slave. Exchange, you begin advertising your link state information. I know Kitale, I know this, I know this. Loading, you start requesting what you don't know. Full, when you've already you've synchronized your LSDBs, so everyone has everything that everyone else has. Okay, so let's now look at the remember we started with the hello packet, so now we are looking at the link state advertisement packet. So how does it look like? So link state advertisements are used to carry the link state information. So it has a number of fields. The first one is called the LS age, and you're going to see it a lot in the practicals. This is the number of seconds. The number of seconds since that packet was produced. So it will always update itself and increase. Then you have the we have the LS type. The LS type. We have 5 types of commonly used link state advertisements. So later on, we are going to explore them and look at what they do. So link state type. Link state ID identifies the link that is described by a link state advertisement. Most of the time, they actually use the router ID for the link state ID field. So again, during the practical, you're going to see that. Advertising router is the router ID of the router that has originated that particular link state advertisement. Then the sequence number is of course just a number that is used to uniquely identify that LSA. In particular, it's also used to avoid duplicate LSAs and also to detect old link state advertisements. So link state sequence number can be used to detect old, because if you have a lower number, it means you're produced earlier. So LS age can be used to detect old, but also the sequence number. Checksum, again, integrity. Then length is also used for, length is used to identify the size of that particular LSA in bytes. Okay. So now let's look at the DR, the concept of the DR and the BDR. So in multi-access networks, the problem is we can have so many adjacencies. Adjacencies means everyone is trying to share with everyone else, as you can see from this illustration here. So instead of letting everyone share with everyone else, we can choose that everyone can share with just RTA, then RTA can share with everyone else. So that will reduce the number of exchanges that we have. What is the problem with these multiple exchanges? The problem is this: unnecessary flooding, repeated LSAs. It wastes resources. It wastes resources. So the formula to calculate the number of adjacencies is normally nx into, actually it's n into n minus 1, then the whole of it all over 2. So for example here, n is the number of routers. We have 4 routers. So 4 into 4 minus 1 all over 2. So you get around 6 adjacencies. And indeed, if you count the number of exchanges we are going to have here, 1, 2, 3, 4, 5, 6. So that is what we call adjacencies, meaning exchanges. If the routers are many, trust you me, it's going to be crazy. It's going to be quite high. So for that reason, we need to elect what we call the DR, which is used now to reduce the number of adjacencies. So reduces the number of adjacencies, the designated router, and also reduces OSPF traffic. Reduces OSPF traffic. So traffic is bandwidth, because if everyone is sending to everyone else, we consume bandwidth. Okay, so how do we avoid a DR as a single point of failure? OSPF specifies a BDR, what you call a backup designated router. Now, to make it clear, a DR, one of these routers is going to be elected as a DR, designated router. When you elect a device as a DR, that device acts as a pseudonode. A pseudonode is simply a virtual. It creates a virtual router so that everyone else is communicating with the virtual router, then the virtual router will communicate to everyone else. So please understand that a DR actually acts as a virtual router. Similarly, a BDR is used to prevent the single point of failure. So when the DR is elected, the BDR is also elected at the same time, and in case the DR goes down, the BDR will take over as the new DR. The BDR also has everything that the DR has, so it can simply pick up and reduce the amount of time that it takes for the network to reconverge after failure. So election rules, can someone remind us how is the DR elected? Someone remind us how the DR is elected, please. Hello? Are we there?
Yes, we are here.
Okay, can someone remind us, please, how the DR is elected?
The interface is the highest priority.
The interface with the highest router priority takes precedence. Now, please understand that OSPF elections are not done per router. They're not done per router. They're done per interface and not router. Interface per interface and not per router. So the interface whose router priority is largest will become the DR. Let me clear this. Will become the DR. So at this particular point, the next criteria is this one. If the interface has the same priority, then the interface with the larger router ID. So after priority, it goes to router ID. Okay, so here we have RTA. It has been elected as the DR. It has a priority of 100. It has a priority of 100. Then we have RTC has a priority of 95, is the BDR. Then these RTD has a larger router ID, but it has not become the DR. Why? Then we have RTB, which has a priority of 0. So what happens? What happens when a router has a priority of 0? Anyone?
It does not participate in the election.
It does not participate in the election. It does not participate in the election. Now, even though this has a high router priority, as you can see here, we have dotted, meaning that on this interface, maybe we've specified it as a different network type, for example, point-to-point. And sometimes when you do that, then it's also not going to participate in the election. So when we don't want a router to participate in elections, we can also specify on the interface, we can specify the OSPF network type as, for example, point-to-point, and therefore it cannot be elected really. Okay, so let's move on to the next one.
Just a moment.
Yes.
When you have a P2P network, I mean a P2P, you specify a router as a P2P.
The interface.
It means that it
router
will not form a neighbor relations. Yeah.
Not the router.
The interface. It means that it will not form a neighbor relation.
No, that's not correct.
The interface, yes.
It will form the neighbor relationship and it will form full adjacency, but there will it will not participate in the election when you use point-to-point. Are you getting my point, Alan?
Yes.
What I'm saying is this.
Yes.
If you have two routers here, RTA and RTB, you've interconnected them. Let me just use this because sorry. Let me use this curved line. Oh, I thought that was a curved line. Wow. Okay. Let me just use a straight line. But please take this as a serial. You've interconnected them using a serial cable. They'll form a relationship. But because it's a point-to-point connection, they don't need to do any election. So they are still going to form an adjacency. They're going to form an adjacency and they're going to exchange their link state information. Are you getting the point? The only thing we don't need here is an election. And in fact, that is what is being said here. So point-to-point, yes, the devices in a point-to-point network are going to form full adjacency. Similarly, in a point-to-point network, point-to-multipoint, they're going to form full adjacency. But do we need an election in point-to-point and point-to-multipoint? No. But in broadcast and NBMA, we only need to form adjacencies with a DR and a BDR. So DR others only form full adjacencies with the DR and the BDR, meaning we have an election of a DR and a BDR. So is that clear now? So we have an election in broadcast networks and NBMA networks, but we don't need DR and BDR in point-to-point and in point-to-multipoint. So that does not mean that OSPF does not work in the other network types. No, OSPF supports all these network types. Okay. I think we're about to end now. Oh, actually we're done. Okay, so can someone assist us with the first question and another person with the next one? A volunteer, please.
Which of the following packets are?
Yes, go ahead.
OSPF packets.
So we have
that question B.
Sorry, I think my network has an issue, so katika kidogo.
Okay, I don't know. There is a hello there. There's that.
It's part of the choices, by the way. I think it's just a typo.
The database description and a link state request.
So okay, so ni gani haiko hapa? Ni gani ni wrong kwa hizi kwa hii list?
Hello, database description and the link state request.
Okay, sawa.
Link state DD and link state.
Link state DD iko. Kuna packet type inaitwa link state DD. Oh, I'm sorry. I think I have an issue with my internet.